on.
Yes.
All right, well, let's get going on the next session. So yesterday, Irene told us about the Swampland with Minkowski. Today, we're going to hear something about Swampland with ADS.
Very good. Good memory. Okay. Hello, everyone. So, indeed, yesterday, the past 2 days, we were explorers, charting the string landscape, Minkowski compactifications, on the quest of some universal feature that is realized in all these string compactifications. So the candidate for that feature is the distance conjecture. And yeah, we're trying first to check if it's realized, but also try to quantify it, right? Like try to understand better what are the, at least within the string landscape that we know, what are the possible nature of the tower of states, what is the possible value of the exponential rates, and so on. So we had the hat, Swamp Rangers, checking more models. Of course, I cannot make justice to all the papers, like has been more than 50 or 80 papers charting this in 1 hour. So this takes years and it still goes on. Okay, there are still corners that one has to explore, things that one has to understand better, especially in lower supersymmetric cases. Okay, so I didn't have time to tell you much about this, but there are also studies with 4 supercharges, okay, in which you already can have a scalar potential, okay. So far, there is no difference with any of the things I told you, okay. And there are also very few, but starting some cases which are really non-supersymmetric in the sense that they are already non-supersymmetric in 10 dimensions, okay? So not only like breaking supersymmetry spontaneously like here, but explicitly, I mean, like there's no supersymmetry at any energy scale. Like for example, there is the O16O16 heterotic string theory. It has no supersymmetry and no tachyons. And you don't know much. I mean, you just know like at weak coupling how the theory looks like. You still have some scalar potential, but at the perturbative limits, of course, you still have the string tower of states. So I don't think it's related to supersymmetry, but this is also part of the, I mean, what is going on right now in the community, okay? Try to understand this better. Anyway, so we concluded after this exploration of the string landscape that it seems this feature that we always have an infinite tower of states becoming exponentially light is realized in all these cases. And not only that, is that in all these cases that are known so far, you can always understand the leading tower, the leading one, okay, so the lightest one that you find, you might have more, but the leading one, there is always some interpretation in some dual frame in terms of a Kaluza-Klein tower or the oscillator modes of a critical perturbative string. This is very powerful because it fixes the possible exponential rates of the tower, right? So this is what has been done in Minkowski. This is the summary of yesterday. And yeah, in particular, I just wanted to make clear, so when you have the Kaluza-Klein tower, right, it's like you have some infinite tower of states. The degeneracy depends on the number of dimensions that you decompactify. So whenever I talk about this mass scale, it's like all of them, right, become light. But then there is like well, this is an integer, okay, this case an integer. Which label the different states of the tower. And you have if it's only one dimension, it's just right like equidistant tower. But if you have more dimensions, it becomes more dense. And for the case of the string, it's so dense that actually the degeneracy per level is exponential, right? We know for the critical string. So in all these cases, it satisfies this bound for the exponential rate. This is what is called in the community the sharpened bound, meaning that the exponential rate of the tower along any direction is always bigger or equal than 1 over the square root of d minus 2, where this is the number of space-time dimensions. And yesterday I was making sometimes some pictures, right? Like you can write like these convex halls of the towers and so on to guarantee that you check all possible directions, infinite distance directions. And this bound is equivalent to the statement that the convex hall of the towers always includes a ball that has this minimum value for the exponential rate. Okay, so this is what seems to be satisfied at the moment. It's non-trivial sometimes how to construct. Sometimes maybe you only have access to part of the modular space because you don't have a flat slice, or maybe even this picture can change as you move in the modular space. So it's not trivial, like try to guarantee that always includes this ball, but that's what happened so far. And just one more thing to finish this. We started the lessons asking the question, what is the cutoff, right, at which the EFT breaks down? So here, right, this lambda that I was writing, it's just identified with the string scale, right? Because in the moment in which I find the first oscillator mode of the string that has higher spin, local quantum field theory breaks down, okay? So that's it. For the case of Kaluza-Klein, you have two scales. I mean, of course, first you find the first Kaluza-Klein state, but that doesn't mean that QFT breaks down, okay? I mean, what it means is that, I mean, you are decompactifying some dimensions, so you need to consider a QFT in higher dimensions. So the scale, when we talk about the scale at which Einstein gravity breaks down, it's actually the Planck scale of the higher dimensional theory. Okay, so it's like you have some hierarchy of scales. Like first you have the first KK, second KK, so on. There is a moment, I mean, you have the infinite tower, it's a moment in which you find the Planck scale of higher dimensions before the Planck scale of lower dimensions. Okay? And that would be the lambda I'm talking about. Okay? So in this case of the Kaluza-Klein, it's just you have the expressions. If I just have one Kaluza-Klein towers, just to make it simple, this is equal to the MKK. We put this in Planck units always, in lower dimensional Planck units. To the ND plus N minus 2. Okay, this is again some concrete power. Good. Since, I mean, today I'm just going to focus on the ADS. I mean, let me just say one more thing because I will not have time, I guess, I think tomorrow. There is also a lot of work on understanding this cutoff purely from bottom up. In the sense that, I mean, here, of course, if we know the nature of the tower, okay, we know it's the string scale or the Planck scale, that's it. But imagine that you are just like some effective field theorist, and I tell you, okay, I found a tower, this is the degeneracy. I don't know what it means, I mean, what is the interpretation in the UV? I mean, I just know what are the masses, but I don't know if it's a K or a string, I don't even want to know about that. So how do you define this lambda? So that sometimes this is called the species scale. Because in the moment in which you have, I mean, in all these cases, you get infinitely many perturbative states that are gonna renormalize the graviton propagator, and the cutoff at which Einstein gravity breaks down becomes lower than the Planck scale by the number of species, which are defined as the number of species that you have below lambda. So it's like you count the tower, up to lambda. So it's like some indirect definition. This is the degeneracy, okay? And you can try as an exercise, like if you take these definitions and use it in these cases, like for instance for the Kaluza-Klein tower, you indeed recover that this lambda is the higher dimensional Planck scale. Okay, so it's like a bottom-up thing. Now, this species scale, I mean, it has some black hole arguments that argue for this behavior, and there were like some sort of perturbative arguments that I think are more like heuristic arguments, how they renormalize the graviton propagator. So for me, the best definition right now actually comes from last year, from papers of Simon Caron Hood from this matrix bootstrap, in which they saw this relation from unitarity and causality using the dispersion sum rule of the graviton. Okay? Okay, good. Any question? Okay, so now comes the moment. So, okay, so this is what we've seen in flat space compactifications. But now the question is, how general is this? Could it be that it's an artifact of the known string compactifications to Minkowski that we have? How can we find out if this is a feature of the string lamppost or is something more general required by quantum gravity consistency? Right? I mean, already that this universal of the compactifications we know is powerful. Okay, so you can already say, okay, from the string theory compactification we have, that's what arises. But we want to do better than that, right? I mean, we are explorers. We want to continue, and we want to understand, yeah, like, can we go beyond string theory, or at least the string lamppost that we are used to? So one way to do that, that I'm gonna talk today, I mean, maybe at the end I tell you a bit about black hole arguments and so on, but what I want to focus is Neri CFT. Okay, so something you can do is, let me say, okay, let me now consider like compactification or ADS backgrounds, let's say. I have string theory in some ADS background rather than CFT, rather than Minkowski, because I want to check whether this is still satisfied here, so that I can translate this, right, to some statement of the CFT, and then work purely on the CFT to try to find out at least whether this is a general feature of any CFT or only of part of the CFTs that maybe have holographic duals that we know, or how general it is. Okay, so I mean, of course, here we are losing something because now we are going to talk only about ADS in a sense, like it's still not our universe, but we can be more general in the sense that we can aim to prove this for any CFT and not just for the landscape of theories that are known, okay? Like just using conformal field theory techniques. So that's the goal for today. And I say, I mean, of course, many of the examples come from string theory, but I mean, I think this is fairly more general, right, than the string lamppost, because we expect that any ADS quantum gravity theory has some CFT dual, regardless of whether we can engineer that from known string compactification or not. That's an expectation. So if that's true, I mean, if we can prove this for any CFT, we will be proving the distance conjecture for any quantum gravity theory in ADS. Yes, I was gonna say. So I'm gonna, unfortunately, I was wondering a lot whether to do it or not. I'm gonna change dimensions because when I'm gonna be talking about the CFT, and then all the typical scale of conformal dimensions, correlators, everything is always written in the dimension of the CFT. So I think it can be very confusing if I change it here. But please keep in mind, okay, that now D is the dimension of the CFT. So the dimension of the bulk is d plus 1. So in these equations, actually, you have to replace a d plus 1. Okay? Sorry about that, but I couldn't find a better way. Okay, good. So let's start translating this conjecture. So first of all, let's talk about the modular space, right? So here we have, we are interested in this scalar manifold, right? The different values of the scalars. Let's focus on the supersymmetric case because this is better here. So then the scalars are massless and we have a modular space. This in the CFT, who knows what it is? Who wants to reply? What is the modular space of the bulk in terms of the CFT? Conformal manifold. Okay, so this maps to the conformal manifold. So if you have a modular space in the ADS, you have a conformal manifold on the CFT, which is the space of exact marginal couplings. Okay. Now, to talk about distances, right, we need a notion, a metric. So in the modular space, we are talking all the time about this field metric from the kinetic term, right? This maps to what is called the Samolov-Zhikov metric. Okay, which is given by the 2-point function of the marginal operators. Okay? So the point is that whenever we have some scalar field that is massless in the bulk, we have some, that maps to having a marginal coupling. And this is the marginal operator, okay? So if you want, maybe, the action, right, in the CFT, you can have a marginal transformation. So you can deform it with this operator, okay? And this is the coupling, okay? This would be the coupling T. Okay? Okay, and maybe let me continue here because otherwise you're not gonna see it. Actually, this is the, yeah, this is fine, yeah, okay. And then the other thing we have to translate is the tower of states, right? So you have a massless tower of states at infinite distance. This translates to having a tower of primary operators. That here we have to be careful. So in the bulk, we talk about massless, right, in Minkowski space. So what is the equivalent of that, no? In the CFT? So in the CFT, the mass, right, gets translated to the conformal dimension of the operator. And there is a minimum value for these conformal dimensions, which is the unitarity bound. So the lowest possible value, which would be the equivalent of becoming massless here, is the unitarity bound. So the point is that the conformal dimension of these operators subsaturate the unitarity bound at infinite distance.
And the lowest mass states in ADS are not massless.
Yes, I was gonna, so now when I go to the scalars, I was gonna, that's what you have in mind, right? Like the BF bound. Yeah, let me just postpone it a second. Okay. So the seems that the CFT, I mean the distance conjecture in the CFT implies the existence of this, like an infinite tower of these primary operators, okay? Operators whose conformal dimension, more precisely the anomalous dimension, so the difference between the conformal dimension and the unitarity bound, must decay exponentially. Let me call it beta maybe, just to avoid confusing now. In terms of the distance measured by Samodchikov, okay, as approaching as any infinite distance limit in the conformal manifold. So this distance goes to infinity in the conformal manifold. Okay, so far so good. Okay, now in practice, I mean, you can ask, okay, can I be more precise about what are these operators? What do they correspond to? Okay. And it seems that there is it's very different depending on the dimension of the CFT, in the sense that if we are dimension equals 2, so this is the dimension for the CFT, so it will be 3 dimensions in the bulk. There's a very different behavior that if we are in dimension bigger than 2. Okay? So in all examples, I mean, let me already give you a result and then I will explain how this is satisfied, okay? But the point is that in all known CFTs, like local unitary CFTs that we know, this is indeed satisfied, okay? And here it works because we have scalar operators. Okay, scalar local primary operators. If you want, the scalar gap goes to 0. And that's from the perspective of the bulk, right? Saturating, and what's happening is that, I mean, you can have mass square that is actually negative for the BF bound, so you're actually approaching from below, okay, right from above. But this is like 3-dimensional in the bulk. But in dimension bigger than 2, which is in the bulk having 4 dimensions or more, that is also what we have studied in Minkowski. Okay. The tower are always higher spin operators. So it's like the higher spin gap, okay, goes to 0. And this really corresponds to having massless higher spin fields from the perspective of the bulk. Okay. Now, if you want to prove this statement, so now it's a statement about how the different conformal dimensions behave as you move in the conformal manifold. If you want to prove this, I mean, or our goal, expectation is that we need to show that there's this one-to-one correspondence between like the infinite distance in the conformal manifold and the infinite tower, right, of operators. So we formulated this like a few years ago, like I think 4 years ago. At that moment, we simply checked whether it seemed to be satisfied in all examples. So it was more like an example-based thing. But since then, okay, like in the past 2 years, for example, this direction has already been proven, not based in examples, but using conformal field theory techniques, like for any CFT that is unitary and local. Okay. Proving for local unitary CFTs. And this direction, so what was proven is that if you have that the scalar gap, in this case, higher dimensions, the higher spin gap, or in 2 dimensions, the scalar gap goes to 0, they have proven that that point is necessarily at infinite distance, and that you have the infinite tower. Okay, like when this gap goes to 0, they have also shown that you have the infinite tower. So it's like this direction here. The other direction, it's satisfied in all the examples at the moment. Okay. But it remains to be proven in general. And this is something that we are working on at the moment. Okay, like try to prove this other direction. It's a challenge also for everyone who is interested. I'm optimistic. I think it's working well for these projects. So it could be that this is, I mean, I really hope, I'm a very optimistic person. So I really hope that this is the last time I give lectures on the Swampland distance conjecture, and I cannot really say like this a distant theorem in the CFTs. But for the moment, this remains to be proven in general. Yes?
Correct me if I'm wrong, but I think we believe that in IoT, there should not be any conformal manifold without supersymmetry, right?
Yes.
All these examples are all supersymmetric.
All the examples we have are supersymmetric. This proof that has been done here does not require supersymmetry, actually. But then in practice, the examples we know are supersymmetric. So yeah, I will now go to like examples and see how this is realized in practice, or to get an intuition of what's going on. Yes. Oops. Oh, that's a pity.
Move it a little more to the middle.
Yeah.
I think when you move your arm, it bumps it.
So it was not recorded. Oops. Now I can see.
I think the recording is probably fine, but
Okay, good. Yeah, that's better.
Can I ask something? So
Yes.
In principle, we expect certain CFTs to be holographic, or like have some to have in
Uh-huh.
this ADS CFT. We don't expect all CFTs to be holographic, but
Yes.
somehow the statement seems to be for all CFTs.
Yeah, so that's a surprise, indeed. So first thing you would wonder is, okay, we started here talking about an Einstein gravity description, right? And asking when the Einstein gravity breaks down, it happens because there is a tower and so on. Now we translate it to the CFTs. When I did it for the first time, I was hoping, I was expecting that we would find out that this was only true in holographic CFTs or something like that. It turns out it's more general than expected. Doesn't seem to be related to having Einstein gravity in the bulk, but seems to work in any CFT, even if you don't have a large N, or you don't have a large gap, or anything like that. Which suggests to me that this feature, yeah, indeed might be like a universal feature required by quantum gravity consistency, right?
But that is the statement I'm confused about. Why would we this seems to be properties of CFTs,
Local CFTs.
local unitary.
So that means that you have gravity in the bulk. Okay, so with local, I mean you have some stress energy tensor. You mean that you have gravity. It's not necessarily Einstein gravity, in the sense that it's not necessarily weakly coupled, like you don't have a large N, or you might also have other higher spin fields in the bulk. So it's not like a.
I thought for the duality you need even more properties on CFTs than just being local. You need large central charge. You need A equals C, that kind of thing in 2D.
That's for holographic CFTs. Yeah, I'm saying that this statement, even if it was motivated from holographic CFT, seems to work beyond holographic CFT.
Yes.
Yeah.
Okay, maybe I'll ask it.
Okay.
There you go.
Mark, yes. What is the property of the CFT at the origin of the conformal manifold?
Because suppose I started from a CFT with compact photon with n copies of compact photon and take the n to the infinity, and before exploring a conformal manifold, it is automatically infinite power.
No, okay, so here what we are doing is, so you have a CFT, so with a fixed central charge. That CFT, so we are focusing on CFT that have a conformal manifold, which means that you can still, right, move in this conformal manifold without changing the central charge. And then you can explore what are the infinite distance limits in this conformal manifold. And then at these infinite distance limits, you find an infinite number of operators that satisfy the unitarity bound and whose conformal dimension behaves exponentially.
So the origin, so you have to start from a CFT which doesn't have the infinite power of and the states that saturate the bound.
You could, no, I mean, the point is that even if you have, the thing is that you can identify some particular infinite tower that whose conformal dimension behave in this way as you approach that limit, and then saturate the unitarity bound only there. Okay, so it's like trying to identify, what is that tower, which would be the equivalent of the tower of states becoming massless, regardless of what other things you might have at any other point.
So in my example, I already achieved this infinite power even before I go to the infinite distance.
Yeah, but if it's a tower which is not changing, right, as you move in the conformal manifold, yeah. So, I mean, you could start at another point, like for instance, this is more like in 2D, right? Like you can have especially higher spin currents, like at any other point and so on. The point is that, like the infinite distance limits are like in one-to-one corresponding with a particular tower. So it's like trying to find which is the tower associated to each infinite distance singularity in the sense that the conformal dimension of this tower varies exponentially in terms of that infinite distance.
Just to clarify, that goes for any generic CFT that I begin with.
If it's local and unitary, yes, and has a conformal manifold.
Still a little bit confused.
Uh-huh.
I have this n copies of a complex code, or my n copies of a equals to one free body CFT. I started with this thing. I already had infinite power of.
You have to be careful also with you start with free bosons and so on in the sense that you need local CFTs also, okay?
What's wrong?
Like you need to have like as I said, like a stress energy tensor in the bulk.
Each C equals to one theory has a stress moment, energy moment of temporary. I can take the n copies and I can still have the energy moment of temporary.
And what's the question then?
Like my theory still satisfies the local unitarity.
Uh-huh.
And it is it has an infinite power of the state operators that saturate the bound to at the before exploring the conformal manifold. So,
Yeah.
there are some theories that saturate this bound has the infinite power.
But you cannot have, so what for instance, this is a paper by Hiroshi and Jifan in 2 dimensions. Like if the scalar gap goes to 0 at any point, at some point, necessarily that point is at infinite distance. So what they have proven in general, so the part that is proven in general, not only based on example, is that if you have a point in the conformal manifold in which this gap is 0, that point is at infinite distance to start with.
So like what is the case that you are thinking about? I mean, if I have just one scalar, C equals 1 theory, then I have that operator, which is a scalar theory. So then my theory is infinite distance away from this theory.
From another point of the conformal manifold, when you have an infinite distance limit, means that any, like if you start at another regular point, any trajectory approaching that point has infinite length. Maybe we can go later through the example in particular. I think there are more questions here, so let's try to, yes.
So in the bulk, I get to the asymptotic value of the dilaton, and that's going to be related to the n in n equals 4, so for example, large n. So can I think of n also as part of the conformal manifold and going to
Okay.
distances there?
Good question. So that's not part of the conformal manifold, so it doesn't enter here. But now that would be like the next step. Like, can we generalize this beyond conformal manifold? Because in Minkowski, I was trying to remark that we know that this works even if you have a potential and so on. So it's not only for massless fields. And actually moving in n is like decompactifying. So you should have the Kaluza-Klein tower. So there are works about that. But maybe you can ask me later.
So how often does it happen that there is no infinite strict tower? Because for me, if I just take some random CFT, it's probably not going to have like So how often does this actually happen that there is no string tower? Are these CFTs rare or?
That there is no string tower. So you are thinking of a CFT that has a conformal manifold and an infinite distance limit, but no string tower. So like dimension bigger than 2, what seems to happen is that you always have a higher spin tower. And whether that corresponds to the perturbative string or not, it's a question that I'm actually hope I will be able to reply. But you have higher spin fields. It means you have some extended object in the bulk necessarily.
So what about the MTV case, like 62 plus 0 or something like this, ADS7 plus S4, like then there is no string tower, right?
Well, you have to find an example that has a conformal manifold, because typically in all this AVM, everything is stabilized. But remember yesterday I was showing this, like the modular space has different duality frames and so on. Even if you start with M theory, you can have some regime of the modular space that has a perturbative string limit, right? So you have to, like the modular space covers different duality frames.
But like changing the coupling is like changing n, right? And I cannot change n by going on the.
Yeah, exactly. So that's why I say, like, first you need to find the conformal manifold. So in that case, the example you have in mind, there is no limit to talk about. But there could be some example of M theory with a conformal manifold, maybe. But yeah, it would. If that exists, it means that there is some direction that the dilaton is not stabilized in a sense, so that you can go to a type 2 error regime, for example. There was another question there. Yeah.
With this infinite CFT tower, are the operators in there? Are they always primaries? Is it a mixture of primaries?
Yeah, primaries. Yeah. Yes. Yeah, that's important. And then if you have a large n, there are also like single trace operators. So that they really map, when you have an Einstein gravity dual, they really map to having like an infinite number of single particle states. Okay, good. I know it looks surprising, but that's what's happening. So yeah, so let me summarize. So yeah, again, like if the gap goes to 0, it has been proven it's at infinite distance. So it seems to be a very generic statement, CFTs. This works in example, but still needs to be proven. So keep attention to archive and these things. So my plan now is to, so let me focus first on this case, okay, dimension bigger than 2. And explain you a bit why this is happening, okay? So I'm gonna let me take the simplest CFT we have, which is n equals 4 super Mills, okay? Explain how it works there, so you get an intuition. And actually, the way it works there is already it already captures the essence of how it's working in general, okay? So it's not just a random example. If you understand this example, then you understand how it works in all the other examples. Okay, so let's focus in CFTs with dimension bigger than 2. So let's take this ADS5 cross S5, sorry, which is dual to n equals 4 super m. Thanks. Okay, so here we have a marginal coupling, which is the gauge coupling, okay, of super Mills. So it's a complexified coupling. And the non-compact part, okay, that is going to give us the infinite distance limit is just the gauge coupling. Okay, this is the axiom. So we can compute the Samorogikov metric here. So the point is that the marginal operator is trace of f squared, okay, plus corrections at the weak coupling limit. So when we approach the infinite distance limit. And the metric is given by this hyperbolic behavior as imaginary part of tau goes to infinity, which is the gauge coupling going to 0. So this is exactly the same type of metric we're getting also in flat space. Whenever we approach an infinite distance singularity, you remember also for the radius, right? It was the derivative over the radius square. And that's what puts that point at infinite distance, because the distance now goes logarithmically, with tau. So this result is general because the point is that precisely the infinite distance limit is the weak coupling limit, so you can just use perturbation theory to compute the 2-point function. And I mean, I'm doing it in equals for super young Mills, but in general, when you have some gauge theory and you send the gauge coupling to 0, the Samouchikov metric will always take this form, And beta is 24, the dimension of the gauge group, which is getting free in the limit, So the point is that as the gauge coupling goes to 0, which is the infinite distance limit, the gauge group, right, the vector fields become free. So we get a free point. Yes? So let me say here clearly. So like the Yang-Mills coupling going to 0 is at infinite distance. And this is a free point in the conformal manifold. So remember the distance, it's just the integral of the metric, right? So just in case it's not clear, I mean, right, if you compute the square root of this, you get 1 over g, and that's why it goes logarithmically with g, so that when g goes to 0, this is at infinite distance. It's clear? So good. So we have the weak coupling limit, it's at infinite distance, and we get a free theory there. Now, we know, I mean, it was proven by Maldacen and Sivoedov, that whenever you have a free sector, you have a free point, you have a higher spin current. I mean, I don't have time to review the argument. Let me put higher spin symmetry better. But yeah, like the point is that the correlation functions satisfy, behave like a free theory. You can show that you have currents, higher spin currents that are conserved, so you have a higher spin symmetry, and they show that you have then like an infinite tower of higher spin operators of increasing spin that saturates the unitarity bound, in this limit. So indeed here, what is happening then is that once the gauge coupling goes to 0, we get indeed an infinite tower of higher spin operators, primary operators of increasing spin that saturates the unitarity bound. So the conformal dimension is d minus 2 plus the spin. And this is a tower of increasing spin starting from 3. Good. This is expected from the bulk because indeed from the ADS perspective, ADS 5 cross S5, right? The gauge coupling square is just the string coupling in the bulk. So indeed, what we are doing in the bulk is to send GS to 0, okay, the string coupling. And we've already seen yesterday, right? And when we do that, the critical string, the type 2B perturbative string, becomes tensionless, right? The string scale goes to 0. So you have all the oscillator modes of the perturbative string that will be precisely dual to this tower of higher spin operators. Okay? So we have the perturbative type 2B string that becomes tensionless. Okay? As simple as that. Now you can compute. I should have done it the other one. Well, that's okay. So here, I don't know, I put beta, okay, for the conformal dimensions, because here in ADS, right, the units that we are using typically are ADS units. It's not Planck units, as I was doing with Minkowski. So these distances and these conformal dimensions are measured in ADS. So if you want to compare the exponential rates with what we have here, you need to translate like to Planck units, okay? So if you do the dictionary, I mean, higher spin operators, let me put delta J, delta J goes, I think, with minus, yes. So since we are a perturbative coupling, outweight coupling, the conformal dimensions always grows as the Yang-Mills coupling square times a function that depends on the spin. And then if you replace you write in terms of the distance, okay, like the canonically normalized coupling, you get that this is precisely, right, because this is logarithmic here, you get e to the minus the distance of Sabamoff-Hikov over beta. Okay, that's the factor that appears. Now, these conformal dimensions, we can translate it to the mass in the bulk in ADS. As I said, we have to write it in Planck units. So this indeed implies, again, like some exponential behavior for the distance in the modular space, where now alpha, which I'm writing everything in Planck units, just relates to this beta by some conversion factor, which is precisely the ratio between the ADS scale and the Planck scale, which is the central charge of the theory. Okay, so in general, you get that the exponential rate of the tower in ADS is 2 times the central charge over beta, that is the dimension of the gauge group. Okay, so this is the central charge. Okay, so, and just to make it clear, so what happens in the limit is that the CFT splits between some free sector. I mean, here it's just n equals 4 superior means, but more generally, in other limits, you could have free sector and a part that remains interacting. I don't care, but there's a part that becomes free, okay? And that's what gives rise to the higher spin operators. Yes?
So when you were saying that the string becomes tensionless, that's in Planck units? Or?
Yes, that's in Planck units. Yes.
Because it's not like alpha prime going to infinity, right?
No, it's alpha prime. Like in terms of the Planck, it's going to infinity, but it's always a ratio, right? Like you have to compare alpha prime with the Planck scale. So the ratio between the two, alpha prime is the inverse of the string scale square. So if the string scale goes to 0 in Planck units, alpha prime, you would say that goes to infinity in terms of the Planck length. Okay, so that's, remember that the string scale in 10 dimensions is related to the Planck scale by a factor of GS, right? So precisely if GS goes to 0, string scale goes to 0 in Planck units, like the ratio goes to 0. And this is the tension of the string, right? String square. Yeah. So that's why you have all these states, like the conformal dimension. I mean, when they saturate the unitarity bound, they really correspond to massless higher spin fields in Planck units. Okay? So the string scale goes to 0. Yes?
Sorry, one logic here. So in the lower equation, you wrote that in this limit, the scaling dimension goes to 0. And in the upper limit, you said that the scaling dimension goes to some constant like d minus 2 plus 2.
Sorry. This I should put here. This is the anomalous dimension. Yes, thanks for asking. So this is delta j minus precisely d minus 2 plus j. No, I put there like. So what deviates the conformal dimension from the unitarity bound? Okay. Yes.
What here? So this higher spin field has to exist in this limit?
Say again?
I mean, another question actually.
Another question. Yes.
So what is the claim here? Is this that the higher spin field have to exist?
Well, this is not claim. This is a result. Is that if you study the infinite distance limit in this conformal manifold, which corresponds to sending the gauge coupling to 0, you get a free point that has a higher spin symmetry, and therefore that means that you can compute the conformal dimensions for the higher spin operators, and they indeed behave exponentially in terms of the Markov distance with an exponential factor that you can compute explicitly. And if you translate that exponential factor to the bulk, that's the result for the alpha. So that's the result.
I'm still a bit confused about the tensionless, because I can still have a weakly coupled string at finite tension, right? But you're saying that this is different, right?
Weakly coupled string at finite tension. How do you define weakly couple? In which sense?
Yeah,
the gauge coupling 0 or?
Yeah, the dimensionless string coupling going to 0, but I can still have like finite tension string. I could pull a convection.
Not for the perturbative string. So if you have a fundamental type 2B string, right? It's a BP string. So the tension is actually equal to the charge. So if it becomes weakly coupled, also it becomes tensionless.
But it's like with the Planck scale, right? Like it's still
yes. Yes, with respect to the string scale, I mean, like these are all, right? It's all with respect to the Planck scale in the sense that when we say the EFT breaks down, it's because we are writing everything Planck units, like from the perspective of the low energy observer. Now, you can, of course, now complete this. So we know that this is the completion is just string theory. And from string theory, nothing goes wrong, right? Like it's perfectly, I mean, precisely this is like the GS equals 0. So you can compute everything that works it. And then if you just measure everything in string units, everything is finite in that sense, right?
But I'm not sure if this is the same thing as like alpha prime going to infinity. But okay, cool.
It depends what you measure with. I mean, what it goes to infinity is the ratio, like alpha prime, right, over the Planck length. That's what goes to infinity, the ratio. Okay? Good. More questions? Yes? Yes, so that's part of, I mean, I didn't have time to review. I mean, there's some paper by Maldacena and Sivoedov in which they show that you have a free point, you have a higher spin symmetry. Having a higher spin symmetry means that you have, well, actually they show that if you have the higher spin operator with a spin 3, then you can construct a full tower, like of increasing the spin. So it means that you have like an infinite tower of operators that saturates the unitary bound. So you have a conserved current, you have a higher spin symmetry.
What about
Mm-hmm.
How did you get the infinite power?
Because here you have the gauge coupling goes to 0, and that's a free point. Like when the gauge coupling goes to 0, the gauge fields, you are turning off all the interactions. So it becomes a free point. And then you just apply this. And in this case, I mean, this is a general thing, but especially in equals for super means, we know like how the higher spin operator, how the conformal dimension behaves with the gauge coupling. But I mean, this also works in other theories, but it's just a result of, it's just because we are at perturbative level. So the first, it's like this is an expansion if you want. Like if you are small coupling, the first term that contributes to the conformal dimension goes as Yang-Mills square, perturbative arguments, and then you might have corrections, but they are subleading if the gauge coupling is small. Okay, so this is the weak coupling result.
So for given spin J, I have like one state that satisfies this.
Yeah, you have increasing spin, like starting from spin 3. I mean, it's like in the Kaluza-Klein tower, right? Like all of them are proportional to the Yang-Mills square, so all of them behave exponentially, but there is like some tower that will depend on the spin. And here there is some function, which can be non-trivial, actually. Okay, good. How much time do I have?
Well, you got 20 minutes.
Same?
20 minutes.
20 minutes, okay, good. Okay, so is it clear how it works in N equals 4 super Yang-Mills? Okay, so what I have written here, it's actually general, okay? All these expressions are general for other CFTs, like Lagrangian CFTs, in which I go to the limit in which the gauge coupling goes to 0, even if it's not SUN, okay, N equals 4 super Yang-Mills. Can have many different gauge groups and so on, lower supersymmetry, N equals 1, N equals 2. If I am in 4 dimensions, like here, sorry, I should remark. Yeah, so this is, maybe, let me write it here. Yeah, for 4-dimensional superconformal field theories, at the weak coupling limits, the story is exactly the same. You are gonna get some free point, has the higher spin symmetry, and the exponential rates are the same and are given by the central charge over the measure of the gauge group. So in the case of, didn't put it in the case of N equals 4 super Yang-Mills, you can replace here the values, and you get that this is 1 over square root of 2. Okay? But in general, it depends on the central charge and the dimension of the gauge group. This is a nice interpretation because it's telling us that the exponential rate depends on what is the portion of the theory that is getting free in comparison, right? Because the central charge includes all the degrees of freedom. This is only the part that gets free in the limit. So I mean, it's giving us an interpretation of what's happening at infinite distance. So you have some sort of decoupling limit that seems bad for gravity. So you cannot decouple from gravity, so that's at infinite distance. And how much you are decoupling from gravity is what is fixing the exponential rate. So in general, I mean, one can conclude that in superconformal field theories, we can have different gauge groups and so on, but if we have some gauge group, as the gauge coupling goes to 0, if this is a marginal coupling, so you have some conformal dimension, this is happening, there is always, okay, these higher spin operators, and the alpha from the perspective of the bulk is always this. So this is a computation of the exponential rates in general for all the 4D superconformal field theories at these points. Okay. Now, since this cannot be bigger than the central charge, so you cannot decouple more fields than the fields that you already have, right? The central charge is always bigger than the dimension of the gauge group. It means that this is always bounded, right? So just from this, you can see that necessarily this is bounded. If I have, for instance, N equals 2 superconformal field theories, one can compute that this is bounded by 1 over square root of 3, and if you have N equals 1, it's bounded by 1/2. Okay, just automatically, which is nice because precisely, we'll see on Friday, but I mean, I'm interested all the times in these upper bounds for the exponential rates because that's what we need for phenomenology, like to tell at least, like you're gonna have a tower that at least decays at that rate. might be that decays faster, so the EFT even breaks down earlier, but at the very least, it will decay at this rate. Okay, so that's automatic already in the CFT. Good. Now, if you compare these values with that one that we have in Minkowski, okay, it's not obvious, okay, that that's satisfied, right? Because this is gonna be, so now this would be the dimension of the bulk, right? So this is 5 in this case, right? So it's 5 minus 2, 1 over square root of 3, okay? One has to be careful when comparing, and that's, I will just tell you with words because I don't have much time, but yeah, the value that I obtained for the type 2B string should actually coincide with this one because it's the fundamental string, so it has the same exponential value of the exponential, the same value of the exponential rate. And the point is that one has to be careful, like here, remember to obtain this value, we're considering all scalar directions, so the radius of the sphere, the dilaton, like all possibilities, while here we are focusing on the conformal manifold that is only sensitive to the dilaton. Okay, so but there is a way using the dictionary, holographic dictionary, to translate these values to this one by taking into account also the dependence on n that is equivalent to the dependence on the radius here. It takes a bit of algebra. I don't have time to do it, but you can find it, for example, in one of the last papers I have about this of the CFT stats conjecture. We have the computation done carefully, and everything matches. Okay. So the conclusion is that when you do this carefully, okay, when you do this map carefully, it seems that this bound is still satisfied in all these CFT examples. I don't know if this might be an artifact of these particular limits, but I didn't find any violation yet, which is interesting. Okay. Good. What else I want to say? So we make one more comment. So for instance, you can now try to get deeper into these infinite distance limits, and you can try to say, okay, let's start classifying, what are the different possibilities that we can have in general. In the same way that in Minkowski, we had a lot of fun classifying the possible infinite distance limits, the possible towers, and so on. So now you can do exactly the same game for CFTs, like not only to get a bound, but really understand the values that appear, okay, and the microscopic interpretation of each of them. So this is very, like, all these things are, this has been done in the past 2 years, so it's only at the beginning. Now we are exploring this CFT landscape, but we are at the very beginning, okay? So for the moment, for instance, we have only checked carefully, like, thinking what is interpretation and everything. For example, theories that have simple gauge factors, in the sense that I have a one-dimensional conformal manifold, okay? Yes, it's like the first step to make it simple. And then these theories in CFTs are classified, okay? So if you have supersymmetry, you have tables classifying the possible CFTs, the possible gauge group, like Lagrangian CFTs you can have. And if you consider, just to make it, because I want to understand what is the bulk interpretation, so if I focus on those that have a large n, so that would have an Einstein gravity, well, not necessarily Einstein gravity, but at least weakly coupled gravity, okay? Not necessarily Einstein. It's funny that there are only 3 values of alpha that appear. So I just wanted to remark this. So you take all possible CFTs and have one gauge coupling and one gauge factor. And have a large n, you compute the central charges, the dimension of the gauge group, and so on. You plug in the numbers, and you get only 3 values. Okay. Now, our intuition from the Swampland, from what we learned before, is that the value of alpha was linked to the nature of the tower. So this suggests that all the CFTs get divided in 3 groups that have a different interpretation for this higher spin tower. So like there are three different types. And one can actually, what we did is you can compute, for instance, the hydro temperature for these CFTs. You see that indeed you have an exponential degeneracy, like you have the string. And the hydro temperature depends, you can write it as a function of this alpha. So you have one hydro temperature for each of them, so that you have some degeneracy of the string for each of them. So this seems to correspond to 3 different strings. So result is that you get 3 different possible strings in the bulk. Okay? Now, what are they? Okay? So here, I'm not requiring that I have a large cap. So for people that know about CFTs, A can be different than C. Okay? These are not holographic. But this value is precisely the one that appears when I have a holographic CFT. So all holographic CFTs have only this value. That is the same one that we obtained for equals for super young mirrors. And that's what corresponds to the type 2B critical string. Okay? So that matches. So that's consistent with the fact that here, when we were focusing on Einstein gravity, the only string we found, right, like all the towers were either Kaluza-Klein or the perturbative critical string. So that string is this one here. But now we are exploring more general CFTs that do not have an Einstein gravity description. They don't have large cap. And we find other types of towers, which are still strings, but these are non-critical strings. So something that, for instance, what we are studying now is to understand better what are these strings in the bulk. So for instance, this one, we know is a string that is a subcritical string that only propagates in 8 dimensions. And you can get it in a similar way to get in little string theory, for example. So yeah, I don't know. So there are more, I think this is also a way to try to understand, what are the possible, understanding the strings is like understanding what is the UV completion in the bulk, right? What is the string theory that we are obtaining? So, yes?
When you say non-critical, do you mean it's still total central charge 0, but...
Yes, exactly. Exactly. So the central charge 0, but it doesn't propagate in 10 dimensions, but in lower dimensions, yes.
So is this a non-critical superstring?
Yes, they are superstring. This is, I don't know if you've seen also, there's some papers by Leonardo Rastelli recently that he was studying some non-critical string. This is precisely this one. And this one doesn't appear that in that paper, but I think we have also a hint about it. You can ask me later. But yeah, there's a lot of things just to point out. This is something that is now ongoing, and one can try to have classifications, right, of these infinite distance limits and what are the strings that arise, and if it's always a string in a sense, right? This higher spin operator. So do we always have some sort of string theory, right, for any CFT? Okay, so that was one comment. Now, I have focused now on 4D superconformal field theories, okay? So you can ask, okay, what about other dimensions, right? Now, the point is that maybe, in practice, I'm afraid that we don't have examples in other dimensions. So, so what about other dimensions? So for dimension bigger than 4, all the CFTs that are known are isolated CFTs in the sense that they don't have a conformal manifold. Okay? Of course, we don't know if that's a matter of the lamppost. That's part of, if we try to prove the conjecture, right? We have to see how much it matters that it's 4 dimensional or not. We can prove it in general for any dimension, so that then we could also exclude these type of things. It's still on the air. But I don't have examples to explore. Okay? So that's why we focus in D equals 4, that we have many, like it's a rich landscape of CFTs with conformal manifolds. For D equals 3, okay, we have CFTs with conformal dimensions, but all the known examples are compact. Which is related to the fact that in 3 dimensions, the gauge coupling is not a marginal coupling, right? So the only marginal couplings that we have come from superpotential deformations in superconformal field theories. And they're typically compact, like because you can just place yourself at coupling equals 0, move a bit away, nothing breaks down. There's no infinite distance associated to that. We have some vague heuristic arguments why that has to be the case in some paper, but I think this is also something that was should prove. It's not clear, okay? It's just a resort of the lamppost for the moment. Yeah, so if we have compact, then there is no infinite distance limit to talk about either. In fact, one could try to be even more, I don't know, if we think, so if one could prove that, I think I erased it, but if one could prove that in higher dimensions, yeah, even in 3 dimensions, the infinite distance limit are always associated to higher spin limits, in a sense, it's like proving that all conformal dimensions in 3 dimensions are compact. Because when, I mean, we cannot have, like with these superpotential deformations, we don't generate like a free theory and we have a higher spin symmetry. So that doesn't work there. So that's also a challenge, okay? That seems to be motivated by this Swampland. Yes?
So if I look the 62,0 or ABJM or something, I still expect a bulk dual with strings, and you're saying I shouldn't expect a moduli space?
Exactly. Yeah, exactly. So what happens is that, yes, so he was asking, imagine ABGM, no? These theories, like, I still have strings in some limit, but the conclusion, right, because these are 3D, the CFT, is that you don't have a conformal dimension. There is no moduli space. So the dilaton, for instance, is always stabilized. So there is no moduli space. So yeah, the couplings associated to those strings are never part of the moduli space. That's what's happening in the example. But that's what one can aim to prove more generally. Okay? Good. Now, for D equals 2, I don't have time to explain, but yeah, there was, as I said, there was also these papers showing that it's not about higher spin, but it's about having the scalar gap, okay, going to 0. And then, interestingly, they show, they also have a concrete value for the exponential rates that they can prove, like some bounds. Let me just give you the bounds to finish. So where do I have this here? Yes. So yeah, they show that there is an infinite tau, so if the scalar gap goes to 0, they show that it's at infinite distance. And then there is a bound for alpha. Well, actually, this would be the beta I was calling, so this is in the CFT perspective. That becomes stronger if you have supersymmetry. So for Susi, is 3/2 over C. So if you translate this lower bound, again to the bulk in Planck units and so on, it's precisely the 1 over square root of D minus 2. In this case, is 1. Okay? So that's, sorry, this is, yes. So if you translate this to the bulk, for instance, this is like alpha is smaller or equal than 1 in Planck units, which is precisely that bound. Yes?
What's on the right and the top part?
1, sorry, this 1. Yeah. And also, interestingly, they also show that when you go to the infinite distance limit, the CFT becomes locally a tensor product of a sigma model on an Rn in the large radius limit and a compact theory. So now you can see, so we're asking, okay, in Minkowski we got these two options, right? Oscillator modes of the string or the Keiki tower. It seems that in the CFTs, for dimension bigger than 2, everything seems related to strings, all the examples we know. But in dimension equals 2 is the other way around. These are like the compactification limits. It's about the scalar fields, it's about the Kaluza-Klein towers. And if I interpret the CFT as a worst CFT, these are precisely, these towers they are obtaining are precisely the Kaluza-Klein towers of the target space. So they are proving that all this, whenever this scalar cap goes to 0 at an infinite distance, you always have some decompactification limit. In that sense, which is precisely consistent, the factors, with what we get there. But that's in general, like for any 2D CFT, regardless of, in general, any 2D unitary CFT. Okay? So that's surprising because, I don't know, like here, I don't know if you realize, like when I'm saying that there are only these two options, it's actually very surprising from the perspective of string theory, because in string theory we have so many objects, right? We have so many different types of objects. This is like just the string. I mean, we have many brains, wrapping brains, so the fact that the lightest one always have this interpretation is very non-trivial. Like some examples of the Calabi-Yau I gave you yesterday, like in the dual frame, in the frame you start with, the Kaluza-Klein tower doesn't look like a Kaluza-Klein tower. It's some bound states of D0 and D2 brains. And also there is another limit I didn't describe, in which the lightest object is an NS5 brain wrapping some 4 cycles. You say, oh, that's completely against this. But then there is always some duality frame in which precisely we know that an NS5 brain wrapping a 4 cycle that is topologically a K3 or a T4 is dual to the perturbative string. So somehow whenever you have an extended object, like a bigger brain that is the lightest one, it's precisely wrapping some geometry that gives you a duality that corresponds to the fundamental string of a Kaluza-Klein tower. That's still to be understood, and that's what we are hoping to try to prove also with the CFTs, okay? So that we can show that, I mean, if this is something general from quantum gravity, or at least quantum gravity in ADS, it's always hinting to the existence of extra dimensions or strings, which is pretty cool. So I think I stop here, right? Thanks.
So it really is string theory.
We see.
All right, before we go to lunch, just a couple of reminders. So tonight, the public lecture is being given by Luca Iliescu. That's going to be here downstairs in one of the big rooms downstairs at 7:30. It's targeted towards the general audience, not towards the TASI audience. It's supposed to be, you know, for non-specialists to understand, but you're all, you know, welcome and encouraged to come. There's not going to be any food or anything like that. It's a little later in the evening, so if you're going to eat, do that before. And then I was just going to remind you that tomorrow is a holiday. Juneteenth is a holiday in Colorado now, and we're not having any lectures tomorrow. So you can do what you want. Is there a question? Yeah.
Do you have the dining, like the cafeterias open tomorrow?
I believe so, right? Yeah. Then there will still be food. Yeah. Can you have dinner? Wait, say that again. Oh, at the UMC. I guess I don't know the answer to that question. Do you know, Ethan? Can they use their? Okay. We do, so officially you have, you know, breakfasts and dinners in one place and lunches at the others. I don't know what will happen. You could run an experiment, but I don't know. All right, we'll see you all at 2.